static and kinetic friction. Chapter 5 for them, I don't know if it was chapter 5 for you or not, but the next thing we talked about was centripetal or rotational or circular motion. When you're going around a curve, when you're going in a circle, it requires a force to do that because acceleration is any change in velocity in a given amount of time. And since velocity is a vector, it doesn't have to be the magnitude that changes. It could also be the direction that changes. So when you go around a curve, your direction is constantly changing, which means it requires a force. Centripetal means center seeking. The centripetal force and the centripetal acceleration are vectors, and they're both pointed towards the middle of the circle. When you round a curve in your car, the force from the friction of the tires in the road is pointed towards the middle of that curve. When you have a ball and a string and you spin it around in a circle, CJ, you did a bucket on a string for your street physics video. That was cool. The bucket was providing the centripetal force, and that centripetal force is pointed towards you, towards your hand. It's always pointed towards the middle. The magnitude of the centripetal acceleration is found with the velocity squared divided by the radius of the circle. So the faster you go, the more force you, or more acceleration you experience. And that makes sense. If you've ever been on a amusement park ride that spins in a circle, you can really feel the effects. And the faster you go, the more you feel those effects. But it also depends on the radius of the circle. So it's harder to make a tight circle than it is to make a wide circle. Was somebody out there asking a question? Going once, going twice. All right, so A sub c equals v squared over r. It's the velocity squared divided by the radius of the circle. Centripetal force is mass times that, because remember F equals ma. A sub c is still a, it's still an acceleration. Centripetal acceleration is an acceleration, so it still obeys Newton's laws. It requires a force to do it, and that force is equal to m times a. Since a, in this case, the centripetal acceleration equals v squared over r, m times that is mv squared over r. So centripetal force equals mv squared over r. It takes more force to move more mass. It takes a lot more force to move it when it's moving fast. And it takes less force if the radius of the circle is big. If you watch racing, like NASCAR, there's different strategies for going around corners. Sometimes they'll take a wide corner so that they can go faster around the corner. Sometimes they'll cut the corner shorter. They can't go as fast, but they don't go as far. So those are the two different strategies, and those are both based on that equation right there.
I have a question.
Yeah.
For the centripetal acceleration and like force and whatnot, I have in my notes that v sub c equals r omega squared. Is that correct? And if so, like, does that kind of double dip into the rotational kinematics? Or like, I just was confused because I also have in my notes that like linear v equals r omega.
All right, that second one is a more universal equation. The first one you listed, I think, is a specific case, probably from one of the labs we were doing. You're putting together equations based on a specific example, but it's not true for all examples, I don't think. Circular motion is rotational motion, but we separate them because we're describing them differently a little bit. We're describing why you're going in the circle in this one, in this chapter. When we're talking about centripetal things, it's why the circle is happening. And when we're talking about rotational motion, we're describing how it's moving in the circle, not why, but how.
So for the difference between like the centripetal force information versus the rotational kinematics, we're not going to have any overlap really in like the omega and alpha and all of that with the centripetal acceleration.
I don't think so. I don't think so. So like memorizing that equation that you listed first isn't going to help you. Understanding what they mean is what's going to help you, because like you read a problem and you say, okay, I'm seeing what they're asking, and it sounds to me like they're talking about somebody going in a circle and what's causing it to go in that circle. If I asked the question, I don't know, I'm just making one up off the top of my head, but if I said, here's the coefficient of friction for a car that has a certain weight, you go around a corner at this speed, the corner has a radius of this. Can you make the corner or do you crash? So there's two parts to this, right? Like, I need to know, one, how much force it takes to go around the corner. That's centripetal force. I also need to know how much force I can provide from the road. And if the force that the road can provide is enough, then I make the corner. And if it's not, then I don't. So by identifying the fact that that is a centripetal force and not a rotary motion type of problem, I can identify which equations to use. And it's just a matter of understanding the concepts. Does that make sense? Is this helping you, or I'm trying not to be confusing?
Yeah, a little bit. I just feel like one of my biggest confusions, I guess, is going and differentiating like centripetal force and like velocity that way versus like rotational motion and
Sure.
omega. And then like sometimes in the rotational kinematics, we also have like the V equals R omega. Like what does that V represent? That's where
Sure.
I'm getting like kind of lost.
Yeah, it's because they're all related. They're all similar. The town I go to, this is a little off topic, but the town I go to in Texas, all of the intersections look the same to me. Like they have the same set of stores and the same color of everything. And at first, I would get lost because everything looked the same. And that's kind of what you're describing, right? Because like it's all similar. It's different, but it's all related. And it's easy to like think you're at one spot and you're actually somewhere else. So hopefully my description now is helping you kind of clarify some of those things. That V in A sub C equals V squared over R is how fast you're actually moving. It's the linear velocity. If you stopped going in the corner, around the corner, if you stopped going on the curved motion, you would be going straight at that velocity. It's the magnitude of the velocity vector.
So then what does like omega stand for?
Omega is how fast it's going around the corner in degrees per second. It's the angle around the circle that you are traveling. It has, regardless of the radius of the circle, that angle is going to be the same. Right now on my table, I'm looking at a Lazy Susan. It's the spinny thing that has like salt and pepper shakers on it in the middle of the table. And there's a candle right in the middle of it. And then there's a salt shaker on the end, and I'm spinning it. And the salt shaker on the edge is moving faster than the candle near the middle, but they're both rotating the same number of circles. If I spin it a quarter of a circle around, they both have gone a quarter of the circle. They both have gone 90 degrees. But the salt shaker was moving faster. The V value was bigger, but the omega value was the same. Omega is the angle traversed in a given amount of time.
Okay, that makes a lot more sense. Would alpha be like the same where it's degrees per second squared?
Yeah, that's correct. So I was thinking about my race car example, and I actually kind of like it. And if this doesn't make sense, just tone it out. But this is something I might use in the future. So some race cars go like high on the track and make a bigger R so they can move at a faster V. And then others will make a smaller R at a slower V. They can't go as fast because it takes more force on a smaller radius, right? That part made sense to you?
Yeah, that helps.
All right, so what if we have two cars going into the corner side by side? We're making a left turn around the track, and both cars are right next to each other. And they actually go through the circle together, and they finish the curve. They get to the straightaway side by side. They start side by side and they end side by side. The outside car had to move faster, but they both have gone through the same angle as they went through the curve. Now, it's harder for that inside car to go faster. It can't go faster because they both have the same frictional coefficients. But the car on the inside, moving slower, still made the same omega because they went around the same curve at the same amount of time. But the outer car had a bigger V, a larger velocity.
That makes sense. So then sorry to like continue this, but for the like units for omega versus like velocity and alpha versus acceleration, would the omega and the alpha be the ones that are using like radians per second? And then the velocity and acceleration would be the ones using meters per second?
So yeah, linear, which would be V and A and delta X, those are going to use meters per second, meters, and meters per second squared. For omega, there's actually some options. You can have revolutions per minute, revolutions per second. That's the number of circles per time. You could also have degrees per unit time, which would be degrees per second squared. The SI unit, the one we normally default to, the one that most physics questions will be looking for, is radians. So it'd be radians per second, and radians per second squared. Most of the equations in that chapter with the rotational motion are built to give you radians in the end. Radians is actually a unitless quantity, so 1 radian doesn't have a unit, it's just a measurement. It's strange. Don't ask me to explain it more than what I just said, because I don't really totally get that. But that's the reason we like to use radians, is because it just kind of works out with other units better.
That helps. Thank you so much.
No problem.
I have a question as well.
Okay.
So for centripetal force, the static friction supplies the inward force. I'm just confirming that. And
Correct.
Is that the same for centripetal acceleration as well?
Yes.
Okay. Thank you.
No problem. Was that Zach?
Yeah.
Hey, Zach.
Hey, how you doing?
I'm doing okay. So I asked that question on one of my tests. It might not have been to you. It might have been in my conceptual class, but I gave a mass of a car. I gave the coefficient of friction between the tires and the curve. I gave the radius of the curve, and I gave the velocity of the car. And I said, given these numbers, will the car be able to make the curve, or will it crash? And a few students got it, but some struggled because they didn't make the connection. A lot of people forgot that in this case, I said it was not banked, so it was a flat curve. So the normal force equals the weight. So a lot of people put in the mass instead of the weight. That was one mistake a lot of people made. But you have to find the frictional force, the static friction, the maximum static friction, because that's the most force that the ground can provide. Then you find the centripetal force, because that's the force required to make the curve. If the force required to make the curve is bigger than the maximum static friction, then it can't make the curve, because the maximum static friction is the most force that the ground can provide. Does that make sense?
Yes.
All right. Did that kind of dig into the question you were asking?
Yeah, it did. I was just making sure I knew the concept. So
Yep.
like if you asked that question, okay.
Cool. All right. Chapter 6 for them was work and energy. I'm trying to remember if that was chapter 6 for us or chapter 7. I think chapter 7 was a momentum for us, but it really doesn't matter as long as we get to them all. So we talked about work as being the change in energy of something. So if I lift something up, I give it energy because I applied a force to lift it and I've moved it through a distance. Specifically, it's the dot product between force and displacement. That means it cares about the parallel components. So I like to give the example of pushing a lawnmower or pushing a vacuum cleaner. Anything that's got a handle that's at an angle. When you push a force down the handle, it's not in the same direction as the motion. I'm pushing sort of down and into the ground as well as forward. So I only care about the part of my force that's in the direction of the motion, in the direction of the displacement. That's why we use a dot product. It picks out the parallel components. Mathematically, a dot product just looks like the magnitude of vector 1 times the magnitude of vector 2 times the cosine of the angle between them. So it's F times D times the cosine of the angle between them. So work equals the change in energy, and it also equals FD cosine theta. We talked about a variety of different types of energy. We talked about potential energy, and there was 2 types of that. There was gravitational potential energy. Somebody's street physics video had an intro to this that was really good. So we had 2 different types of potential energy. One was gravitational potential energy, which is m times g times h, mass times the gravitational acceleration times the height above the 0 point. 0 point is whatever 0 reference point you pick. That can actually get complicated. like, you don't have to listen to this part, it's not on your test, but it gets complicated because in astrophysics, we use our 0 point for energy being infinitely far away, and you get more energy as you get closer. But when we're looking at like everyday life at the macroscopic scale here, just like a jar sitting on a table or something, then we normally pick our 0 point at ground level. So it's kind of the opposite, which can get complicated. But we didn't really get into the weeds on that one very much. We just said MGH was usually 0, or H of 0, height of 0 is on the floor or ground level. But you get to pick what 0 is. That's kind of nice. We also talked about elastic potential energy. Elastic potential energy is 1/2 kx squared, where k is the spring constant, x is the deformation of the spring, or whatever the elastic thing is. So it's if my x is 2 centimeters, then I have stretched or compressed the spring by 2 centimeters. So again, potential energy for a spring is 1/2 kx squared. K is the springiness of the spring. And there was 2 types of kinetic energy as well. We had linear kinetic energy, I think, or I just called it kinetic. Translational kinetic energy. It's just the normal kind for straight line motion. It's 1/2 mv squared. For rotation, we just substitute in our rotational variables, 1/2 I omega squared. So Caitlin, there, that would be the radians per second, the omega. And I showed you that like in effect with the Tic Tac, because once it spun, it didn't bounce as high because it had rotational kinetic energy. And when it stopped spinning, it bounced higher, like a football. An onside kick in football, those are pretty cool. Questions about that?
Could you tell us what the number for spring constant is?
There's a couple options on that front. If I just gave it to you, like K equals whatever, it's newtons per meter, that's the unit for K. Or I can say I use 5 newtons to stretch a spring 5 centimeters. You can find the K value because spring force equals negative Kx. The force that I'm applying would be equal to the negative of the spring constant. So 5 divided by 0.05 would be equal to K.
Okay.
K equals negative Kx, you can just find K. So either of those would be an option. Either I
Okay.
give it to you or you have to find it using the basic equation.
Thank you.
Yep, no problems. I didn't recognize that voice. Who asked that question?
Gabrielle.
Awesome. Thank you, Gabrielle. Right, next, I believe, was the momentum chapter. Where's chapter 7? Where are you? Oh, there it is. Yep, momentum. All right. A lot of street physics videos on this. So I think a lot of you got a chance to study this a little bit. And a lot of your real world physics problems had momentum in it too. So call that a win. That's the whole point of doing those projects, to make you review and think about it a little differently. They say you don't really understand it until you try to teach somebody that thing. And there's a lot of truth to that. All right, momentum, also known as a quantity of motion, a quantification of moving objects, equals m times v. The unit is kilogram meter per second. It's a vector, so it does have direction. It's in the direction of the velocity. Because remember, mass is a scalar quantity, and when you multiply a scalar times a vector, you get a vector in that same direction. So P equals m times v. A change in momentum is called an impulse. Impulse equals the force applied to cause that change multiplied by time. So delta P equals F times T, which is just a special case of Newton's second law. It's just a doctored up version of F equals ma. So delta P divided by T equals F, and delta P is equal to delta mv. So delta mv over T equals F. Delta V over T is A. So it's just F equals ma. They're identical equations. They just look a little different. We did talk about conservation of momentum, which is a result of that equation we just talked about. If there is no outside force, then there is no change in momentum. If delta P equals F times T and F is 0, then delta P is 0. So there's no change in momentum if there's no outside force. If there is an outside force, then there will be a change in momentum. Because of Newton's third law, if there's a change in momentum of one thing due to an outside force, there's going to be an equivalent change in momentum to the thing that caused that force, that caused that change. Whew. We did talk about collisions as well. It's kind of a spectrum. There's perfectly elastic on one end, which is a conservation of both momentum and kinetic energy. It's not really possible, but we approximate it with like pool balls or metal balls or the Newton's cradle. Atoms go through relatively elastic, nearly perfectly elastic collisions. Excuse me. On the other end of the spectrum is perfectly inelastic, where a pretty substantial chunk of that energy is dissipated into the environment in the form of heat. That's when objects will hit and stick together. And I think that's all we talked about in that chapter.
So in the inelastic, there's no conservation of kinetic energy.
Correct. All right. Chapter 8. Oh, sorry, go ahead.
Sorry, could we go over like the impulse and inelastic, or no, can you go over the elastic and inelastic equations? It's like
well, there's no specific equation for those things. What there is a conservation of momentum. And if I have an elastic collision, whatever the total momentum beforehand is going to equal the total momentum afterwards. Now, if they hit and bounce off of each other, there's a bunch of different options, but I have to add up the total momentum beforehand and then use that to find the momentum afterwards of the things. So whether it's elastic or inelastic, you follow the same process. I'm going to jump over here. So I got object 1 and object 2, and object 1 comes in and bumps it. And let's say they hit and they bounce off of each other like that. So this has M1, this is M2, this is still M1, this is still M2, this is V1 initial, V1 initial, V2 initial equals 0, V1 final, V2 final. Maybe I don't know what V2 final is, but maybe I do know all the other stuff. I know everything else. So momentum before the collision is going to equal momentum after the collision. So M1 V1 initial plus M2 V2 initial is going to equal M1 V1 final plus M2 V2 final. Okay. If it's perfectly elastic, then there would be conservation of energy as well. Yeah. That was that hockey player problem that took a bunch of algebra to put the two equations together. Mm-hmm. I'm not going to make you do something that algebraically demanding. That's just too much to ask for one exam, one question. Yeah. But well, this is 0. So we get M1 V1 initial equals M1 V1 final, but it's a vector. Remember, momentum is a vector. So these are vectors, and those velocities are vectors too. So V1 is a negative number. Mm-hmm. If you had something like this, you would have to make sure that that's negative because it's bouncing in the negative direction. I've established right to be positive. That means anything going to the left is going to be negative.
Yes. And I'm just confirming, like for an inelastic, it would be the same beginning formula, but then we'd have M1 plus M2 VF on the right because they stick together and go like one velocity. So I'm going to draw the same picture, but in this case, they hit and they stick together and they move. We'll just call it V final. Technically speaking, you could use the exact same equation if you really wanted to. Like you don't even need a different equation, but in this case, that final velocity for V1 is the same as the final velocity for V2, right? Yes. Because they're moving together. So yeah, I'm going to write it both ways and you're going to see that it's actually the same. M1 V1 initial plus
M2 V2 initial, which is 0, equals M1 V1 final plus M2 V2 final. If they're stuck together, the two velocities are the same, right?
Yes.
So that's just V final. So I don't need V1 and V2 final, I just have V final. And since it's V final in both terms, you can factor that out.
Mhm.
So you get M1 V1 initial equals M1 plus M2 times V final.
Okay, hold on, let me write that down. Yeah, I just wanted to refresh that because I remember.
Yeah.
I remembered it.
That's what we're here for.
Yeah. Thank you.
No problem. So actually, this is where it diverges a little bit, because you guys had an equation, or a chapter on static equilibrium next, where they went right into rotational motion. So static equilibrium was like the problem with Spider-Man hanging from the signpost, or the bridge that was collapsing. Anytime both the torques and the forces add up to 0, then you have a static equilibrium. You get to pick whatever convenient rotational point you have, but all the torques will add up to 0. The net torque is 0, and all of the forces will add up to 0. So the net force equals 0. That means the clockwise torque and the counterclockwise torque all add up to nothing, and the positive and negative x forces are the same, and the positive and negative y forces are all the same. And we can use that to figure tons of information out about static equilibria situations, which we did. We did a bunch of examples of that.
I know I struggled with this, so I was wondering if we could go over like a problem.
Sure.
Can we do one that was like the Thor problem on that quiz?
Sure. Let's do that same problem.
Yeah. So
So we were given the force downward. I don't remember what it was, but we were given force gravity on this. There's an attachment to a building over here, or yeah, there's like a building over here it was attached to. And then there's a web line with Spider-Man. And then we had superhero Thor holding the building up, or holding the bridge up, but right on the end. Let's put that right on the end. The force was applied right on the end. It's Thor as his hammer. All right, cool. All right, we were asked to find what Thor's force was, but we were given the tension in the rope, right, or in the web line. So part A was asking to find the force that Thor was applying, given that information. And part B was to find the force that the building provides. And that's important because like given materials will only provide, they can only provide so much force before they fail. So if you're building a bridge, if you're building a building or whatever, if you're an engineer of some kind, it's important to know how much force something can provide and how much force it would be required to provide given a certain circumstance. So you know what its tolerances are. So you'll know when it's going to fail. So we'll call this F B for F from the building. And we'll call that F Thor. All right. We did a bunch of problems like this, and I think people got mixed up, but it's really no different than all the other problems we've done. So we know the length of the, sorry, team, hold on for 1 second. I'll be right back. Somebody's knocking on my door. I'm back. We know the length of the entire thing, the bridge. So we know how far away Thor is applying his force. We know that, I think it was like 5 meters. We know the distance between Spider-Man's web attachment and the end. So we actually know the distance for that lever as well. Good, yeah.
Yep, good so far.
I'm erasing this so I have a little room to work. But we know that that's the length L. And then the length for Spider-Man is going to be, if his line is X meters away from the edge, that's going to be L minus X for Spider-Man's distance. So the torque that's clockwise will equal the torque that's counterclockwise. If he's holding it up, it's at static equilibrium. The clockwise torques, the ones that make it go in the direction of the clock, there's only one. It's the force of gravity on the bridge pulling down. So it's going to be Fg for the bridge times L over 2. We don't have to worry about the sign of the angle. Torque is equal to R cross F, which is RF sine theta, but all the forces, that force there is 90 degrees. Not all of the forces are. So like this one, we're going to need the angle. But I think the angle was given in the problem. The counterclockwise torques are the ones by the superheroes, the ones holding it up. So we have the torque from Spider-Man, which is going to be the force from his web line, which is the tension, times the distance, which is L minus X, times the sine of the angle theta. And then the force for Thor, the torque from Thor is going to equal the force from Thor, which is what we're trying to find, times the distance from the pivot, which is just L. And I believe everything was given in that problem except for this F Thor. So now this is it. That's it. That's all the setup that's required. At this point, we're just going to do some algebra.
Yeah, I'm just making sure that the first torque on the counterclockwise is Spider-Man. So it doesn't have a subscript on it.
Yeah. Yep.
Okay.
So this is the bridge. This is Spider-Man. This is Thor. And it doesn't have to be, that could just be a crane with a cable. Like Spider-Man is just a creative thing to put in there to make it a little bit fun. But it's just, there's something providing a force. It doesn't matter what it is. There's a pillar here or a superhero, but whatever it is on the end there is pushing straight up with some force, and we're trying to figure out how much. So yeah, you just plug in the numbers and solve for that last force. FYI, I have about 40 minutes and then I've got to go. It's kind of a hard deadline. I've got to meet somebody. So we'll get as far as we can. I'll answer all the questions that I can. Is that fair?
Definitely fair.
Okay. If you have other questions and you want to ask them, you can email me and I will try to get to them in between my meeting and my grading. I will do my absolute best. So let's not waste any time. Should we continue on and do the second half of this problem too?
Yeah, I have trouble with the forces part.
Okay. So the key here is dividing them into X and Y components. So I'm going to put the X's in blue and the Y's in yellow because those are the two colors I haven't been used yet. In the X direction, there are only two forces that are in the X direction. There's an X component of FB. So there's FB in the X direction, force from the building, and there's a force from the web line in the X direction. So in the X direction, there's just a left and a right. To the right is going to be FB in the X direction, which is going to equal the force to the left, which is the T in the X direction. So FBX is going to equal the X component of the tension force, and that's going to be T times the cosine of theta, because it's the adjacent to the angle. In the Y direction, we have more forces than that. I'm going to draw them in yellow. We have an upward part of the building force. We have an upward part of the tension force. We have an upward force from Thor, and we have a downward force of gravity. So in the Y direction, the ups equals the downs. So in the up direction, we have FBY plus T in the Y. That's the tension from Spider-Man, plus Thor, which you just found. And that's going to equal the gravitational force on the bridge. So FBY is going to equal FG minus TY, which is T times the sine of theta. I had to think about it for a second. Minus F Thor, which you found in part 1. All right. So you plug in your numbers. You plug in the tension force times the cosine of the angle, both given in the problem, and you'll get FBX. You get the X component of the building force. You plug in the weight of the bridge, the tension force, the sine of the angle, and the force from Thor that you found in part 1, and you'll get the Y component. Once you have the X and Y components, it's just another example like we did, like Caitlin's question. We just have to add the vectors together. Once I have the X component and I have the Y component, I can find the resultant FB. And I can find the angle.
Do we use the Pythagorean theorem for that? Or?
Yeah. Once I have an X component and a Y component, I have two sides of a right triangle. The third side, the hypotenuse, is just the square root of FBX squared plus FBY squared. And the angle is the inverse tangent of FBY divided by FBX. It's what we did way at the beginning. It's this.
So for theta, it's tan inverse of opposite over adjacent.
Yep.
Hypotenuse.
Yep. Okay. You feel better about that?
Yeah, I do.
Good. All right.
Yeah,
Awesome.
thank you.
No problem.